In the last video, we ran a goodness of fit test where all the proportions were different from each other. So each category had its own different proportion. Let's see one where they're not all different. Let's look here. An article in the Sunday Times, May 16th of 2004 stated, quote, "The planets may control your future after all. A renowned astronomer has broken with scientific orthodoxy to claim that astrology could have some basis in fact. This year's Sunday Times Rich List included an analysis of the star signs of Britain's 1,067 richest people." Why they picked 1,067, who knows, but whatever. Finding significant differences with 110 born under Gemini, but only 73 under Pisces. Dun dun dun. So this is the star signs, your horoscope. And so they're trying to say, hey, maybe Gemini is more likely to be rich than Pisces. Pisces, poor Pisces, only 73. So is there a reason to believe that the article is correct and there is a significant difference between the different astrological signs? So I have the computer output below right here, and I can actually run this also with the calculator. We have our observed values right here. And then I have my test proportion. Let's talk about where that came from. So I'm assuming that this is going to be kind of strange. I'm actually going to do the null and alternative hypothesis first, and then I'll come back to do part A right here. So what do you assume about star signs? There's 12 of them, Gemini, Taurus, Aries, Capricorn, and so on. There's 12 of them, and you assume that rich people will be evenly distributed because these star signs are evenly distributed in the calendar. So you assume, hey, they're all going to be equal. So I assume that the proportion for each sign is a 12th. And I didn't even bother writing it out. Like proportion for Pisces equals the proportion for Capricorn equals the proportion for Taurus, blah, blah, blah. And they should all be 1/12 because there's 12 star signs total and they divide the year up evenly. And the alternative to that is that the proportion for each sign is not all equal to 1/12. Or in other words, at least one of those proportions is significantly different. Or you could say the distribution of proportions is not what was in the null hypothesis. So again, there's lots of ways to write that. But this one's particularly easy since you assume that they're all equal. The alternative to that is that they're not all equal. Somebody's different than the rest. Okay, so that test proportion is what I have right here, that 0.08333 repeating, right? That's what you're assuming. You're saying, hey, I expect 8.3% in each one of these. So let me find the expected value in one category. Let's just start there. Let's start with Gemini. So the expected for Gemini would be n times p, right? So n times p. But n is 1,067 because that's the total for the whole group. They pulled 1,067. You can see it right down here. N is 1,067. They also said it right here. It's 1,067 for your n. So I'm going to take 1,067 and I'm going to multiply it by my proportion, which is 1/12. So let me grab the calculator and quit out of here because that's where I'm at, and take 1,067 times 1/12. And I get 88.916 repeating. And it would be that way for every single sign. They would always be the same because you assume that they were all equal to each other, right? So this is 88.916 repeating. That's 6667. The 7 is because of the rounding at the end of the number. Okay, so that should be my expected value for every single one of these. They should all be expected value of 88.916 repeating. And there I have them right there. Now I'm just going to go back to the calculator and show you how to do this one more time with that. So if I go to Stat and I go to Edit and I type in all my different numbers, so I'm going to have to go up and clear this out and go over here and clear this out. Okay, so I would type all these up, what I had from the output. Now, luckily for me, they gave me the output. Otherwise, you wouldn't be able to do this. But they gave us this particular output, so we can do this. There's our observed. Then for our expected, what I want is 1,067 divided by 12. And then I just want it again and again and again, right? All right, so let me type in all of those. 1 second. There they all are. So then I would go to Stat. I would go to Tests. Goodness of Fit Test down here. And then choose that. My observed was an L1, my expected is an L2. My degrees of freedom is 11 this time because 12 take away 1 is 11. I'm going to go down to calculate and press enter. And there you can see 13.574 and 0.257 is our p-value. And that's exactly what Minitab gave us right here. See the 13.5736 and 0.257. Now the degrees of freedom, we just showed where that came from. That was 11. And that was calculated by taking the sample size, or excuse me, not sample size, the number of categories. So k take away 1, that would be 12 take away 1, which is 11. Right, so that's where that came from. Like that. All right, then we want the test statistic and the p-value. So the test statistic is this chi-square value right here, and the p-value is the one I just put the green box around. So let me type those up and highlight them 1 second. And there we have it. The test statistic is the chi-0 squared, which is 13.5736 approximately, and the p-value is approximately 0.257. And just real quick before we go on, I want to take a moment to show you how to do this with StatCrunch, just in case. So let me type up our values right here. So I'm going to call this OBS right here and EXP, just so I can keep them straight. I can call it OBS2, observe 2. All right, I'm going to type all these numbers, 110, 104, 95, 92. Okay, so those are all in there. And then I want to get all these numbers the same. So 88.916 repeating. I wonder if this will do a division. Let me type it. Nope, it won't. You'll have to type it in. All right, so let me go type these in and I'll be right back. Oh, one real quick trick. I noticed that I could copy. So I kind of went up in here and clicked a couple times and I kind of copied that value. And then I click on the next cell and paste. Control V, Control V, Control V. There are other ways to manipulate StatCrunch, but this will be quick. All right, so that's that. Then I'm going to go to, I don't need this one anymore, so I'm just going to close that. Stat, goodness of fit, chi-square test. My observed is an OBS2. My expected is an EXP2. Or you could just do this one because you assume they were in equal proportion. See that? That'll be an equal proportion test. That'll be better, actually. And then let me go to compute. And then see, look, I found the 88.666. And that is not the same, and that's because I messed up. Look right here. It should be 88. I'm going to go back here and edit. I'm just going to cancel this. I got to retype this. This one was 88. All right, then let me try again. Edit, compute. There we go. 88.916. So it was kind of nice on this particular one. I had this option of I could pick it. If they were all different ones, I could type them into my own column. But I also have this option of just assuming everything's equal. And then when I click compute, it figured it out for me, which means I actually didn't need this entire column. It all is unnecessary. I can go to, let's see, edit, columns. I can delete, and I can tell to delete that column. It won't make any difference to the test. Right? I didn't actually need that column for this test. This other one, I did need the columns because they weren't all equal. In the assumption case, the null was not that they were all equal, whereas this one was. Okay, so that's nice. Good to know. So let's see here. There we have it. All right, so this is a pretty high p-value, 0.257. So I'm betting we are not going to reject the null hypothesis, but first things first, we're going to have to draw our lovely picture and label it and everything. So remember your degrees of freedom is 11. So if I go to the table, the chi-square table, and I look at degrees of freedom as 11 right in here, and then I think about my chi-square statistic, which is about 13. So that's a little bit closer to this right-hand side. So we're a little bit on the right-hand side, which makes sense because you have 0.257 of your curve shaded. So it's going to be a good amount of your curve shaded. And remember, if you have the 84 calculator, you can actually do this with the calculator. Say stats. There we go, goodness of fit test. And just run to the bottom. Make sure you have the correct degrees of freedom in there. And instead of calculate, click on draw. And it'll draw the chi-square curve for you. So there's the chi-square curve with 11 degrees of freedom. Still right skewed, it's not normal. And there's the picture, that's what it should look like. This line right here where it stops being shaded, that's 13.57. You can tell because the tick marks are each worth 1, right? You're halfway between 13 and 14. And that area we just shaded is 0.2575. So let me draw a picture for that and paste it into our lovely notes here. I'll be right back. All right, there we have our picture right there. So we have our chi-squared, it's technically chi-0 squared, but I didn't have the ability to put the little 0 in there. It's 13.5736. That's that vertical line right there. And that area is 0.2575. So if the researcher set alpha to be 0.05, that would not be a statistically significant result because your p-value is not less than your alpha. That means you would not reject the null hypothesis, which is not a significant result, right? I mean, remember, statistically significant means getting to reject the null hypothesis. That's what matters to us. So if you're not able to do that, that is not significant to us. Okay, now what conclusion would you reach then? Well, despite what the article claims, there's actually not enough evidence to support the claim that the distribution of astrological signs is not even amongst the wealthy, or not evenly evenly distributed is what I'm about to say, but I already said distribution. In other words, Geminis are no more likely to be, in other words, there is no evidence, there is not enough evidence, not no evidence, there is not enough evidence to support the written statement that Geminis are more likely to be wealthy, very rich, than Pisces. Right? Geminis and Pisces is, I don't know how to say that correctly. People that are born under the Gemini sign are more likely to be very rich than Pisces. People born under the Pisces sign. All right, now I kind of threw this one in there for a little review, but it's a good thing to remind ourselves. If the decision we're making is not correct, what type of error will we be making? And that would be a type 2 error. I just threw a little explain in there. So a type 2 error is when you do not reject the null hypothesis, but it was actually false and the alternative was true. So since we did not reject the null hypothesis, the only error we could be making is a type 2 error. All right, we're done with that section. We have finished with goodness of fit tests. And you've seen both StatCrunch and the TID4, and you've seen ones where the distributions were all equal and ones where the distributions were not all equal. But they pretty much work the same. Don't forget that they're always chi-square distributions and they're always right-tailed no matter what. And you will never be doing this stuff by hand. You'll be using computer output to help you. In particular, we don't do step 3 by hand. Let me grab step 3 real quick. Here's the test right here. And we are not doing this step right here, finding all that stuff by hand. Not doing it. We'll make the computer do the heavy lifting for us. All right, we're all done there. I'll see you back here for a trip down memory lane to chapter 4.4. We're going to talk about contingency tables, which is actually not something we saw when we originally covered chapter 4 much. We saw it a little bit, but we're going to get in bigger depth now. See